Python has three main tools for scientific computing. NumPy, which allows you to look at large numerical datasets, SciPy, that allows you to do heavy mathematical analysis, and Matplotlib, that allows you to analyse and visualise that data. The first thing we need to do is to install those pieces of software. So to do this, we follow these commands. We type the red commands into our Python window. Now I'm working remotely on the Raspberry Pi, but you'll see a different desktop when you're working on the Raspberry Pi itself. So let's type this in. Now you'll see it takes a little bit of time to do these installations. Okay, that was relatively quick because I had already installed it. Let's try the next one. It's asking us whether we want to continue. We say yes. Okay, next we'll install this stats models, which is something to go with SciPy that allows you to do some of the statistical modelling. Oops. Sudo apt-get install Python stats models. Oops. There's a spelling mistake there. Yep. Again, we need to wait for this to run. So now those are installed, we can launch Python by typing Python, pressing enter, and Python is launched. So what we want to do now is import the module that allows us to do the basic mathematical analysis, NumPy. We did this by typing import NumPy, and we want to give it a little handle, a little name we can call on when we want to use its module, use its commands. So we'll import it as NP, a shorthand version for NumPy. So what this then allows us to do is to start making things that look a little bit like an Excel spreadsheet, but aren't visual. So if you think about the situation where you've got an Excel spreadsheet, it's great if you're working with a few dozen numbers, a few hundred numbers, but often these data sets will be using a much, much bigger. If you think about the situation where you're working with a column that's 1 million numbers long, it would take you forever to scroll forwards and backwards through them. This is a situation where using Python, using NumPy, using scientific computing makes a lot of sense. So we can create that list of 1 million numbers very quickly. We call a list of numbers an array of numbers. So I'm going to call the variable that holds this information my array. So my array is equal to, so it holds the information generated by this command. And the command is np, so numpy, dot a range. And that means produce an array with a range of numbers, and the range of numbers, the numbers we want, go from 0 to 1 times 10 to the 6, 1e to the 6, and that's 1 million. So we've just created a list of 1 million numbers. And what we can do is we can start to look at those values. So if we go print, it doesn't print to a printer, it prints to the screen and displays the values within the variable my array. What you can see is it only displays the first 3 numbers and the last 3 numbers. You can see the last number is 9,009, yes, no, 9.99999 times 10 to the 5, so one value below 1 million. And the reason why it doesn't actually go to 1 million is because it starts at 0 rather than at 1. Okay, so you can see how quickly that worked and how quickly we can start to interrogate this data set. we can start to do mathematical operations on this data set. So a simple thing we might want to do is calculate the mean of the data set. So we can say that, where's the data we want to work with? It's this variable called myArray. And what we want to do is the mean. So the brackets at the end mean it's a function. We're performing some operation. So we want to find out what the mean value of the values held in myArray are. And you can see very quickly it comes back and it tells us what the average value is. You could have guessed what that value would have been. It's not just the mean, we can work out a whole bunch of other things. myArray dot max. Again, we'll put the brackets at the end. The maximum value, as we knew, is 1 shy of a million. And of course we can do the same thing. What you saw there was me using the arrow keys. Rather than retyping, I can press the up arrow and it goes back to the value, the command we had before, and I can edit it. So I can say I want to see the min value, the minimum value, which as we know is 0. Now we can start to perform mathematical operations. So for example, we might want to times our array by itself. We might want to times every value within our list of numbers by the same value in an identical list of numbers. Let's just start. What we can do is print 5 star 5. 5 times 5 is 25. If we've got a list of numbers, we can do print myArray times myArray. And what you can see is the values, 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4. Right the way through, and you can see that we've got values times 10 to the 11, so just shy of times 10 to the 12, which would be a million times a million. And of course we can calculate the mean of these values. An alternative way to calculate the mean is to say we want to print the numpy.mean. So using the numpy function, we can calculate the mean of this array times itself, and we can find that value there. So you can see very quickly we're doing operations with very, very large data sets, and it's not struggling at all. You can start to see the capacity here. You've got to work with extremely large data sets in extremely efficient ways. Okay, now we start to think about how we can visualize data. Because when you're working with these large data sets, you can't just sit and look at the values. You have to display it in some simplified form, which is often a graphical form. Figures, plots, those sorts of things. So to do that, we're going to import the matplotlib function. So we're going to type import matplotlib. Now actually matplotlib has a whole bunch of things it can do, and we're just interested in its plotting abilities. And they're called they're a sort of subset of the library called pyplot. So, and again, we want to simplify that. We want to have a shorthand name to describe that, so we're going to use plt, sort of plotting functions. So it takes a while because we're just working on a small Raspberry Pi, but now we've imported all of the plotting functions and they're available for us. So let's look at again at, well, let's create a new array. So myArray, we could call it whatever we want. Let's call it myArray2 to distinguish it from what we had before. Now here I'm just giving you a different way of creating some values. What I want to do here is create 200 values that fall in the fall between 0 and 6. So a linear spacing of values, numpy.linspace, between 0 and 6, and I want to subdivide the values from 0 to 6 into 200 parts. So let's now print that and see what it looks like. myArray2. What you can see is we've got 200 values, and they fall between the value 0 and the value 6, and they're evenly distributed. Okay, now we want to perform some sort of mathematical function on this data set. It's a relatively small data set, but you get the point. So let's have a further array. Let's call it second array. and we want that to hold the value of the sine. So if you're not familiar with sine, look that up on Wikipedia. So the sine of the values we've got. So numpy.sin, sine, shorthand for SINE, my array 2. And you can see straight away it's done that mathematical operation. And again, we could print, excuse me, I'm going to sneeze. We're going to print the value of the second array. Now what I did there was to select what I was interested in and just click the middle mouse button to paste it. Okay, so that is the sign of those values. As you can see, they all fall between 0 and 1. So what we want to do now is to plot that data. So I'm going to type plot, plt, which is our shorthand handle for the plotting functions within matplotlib. And one of the commands that has within it is plot. So we want to plot, first of all, our values from 0 to 6 on the x-axis, so my array 2. So those are the x values, and the y values we want to be the sign of those values, so the mathematically transformed values. So we'll type second array, which is what we called the array that holds that data. It takes a little while because, again, we're working on a Raspberry Pi. It doesn't have any heavy processing. And now we want to show that. So what we do is say, well, we want to use the plotting functions that we imported. And again, there's a command to display the maths that you've done, plot.show. And you can see that there. It's come out as a nice window containing the sine curve associated with the values from 0 to 6. We can close that by pressing the button here. Now it might look a little bit different on your computer because, as I said, I've logged into this from my Mac to make things a little bit easier to record this video for you. Okay, we can go a lot further. We can do all sorts of very fancy graphics. I'm not going to run through this, but using just a small number of lines of code, you can start to produce 3D surfaces, you can produce 3D scatter plots, you can produce animations, you can produce an awful lot. And I'll direct you to this link here to see the kinds of plots, the kind of analyses that you can do. Okay, the second thing we're going to do is look at SciPy, or at least the statistical tools which we've got to analyse data. So here we're going to import statsmodels.api. So .api means some subset of stats models that we're interested in. And we found out we're interested in it because we simply just looked online and we saw, or we looked for instructions for how to perform a simple ordinary least squares regression. Now the reason we only import part of the tool rather than everything that stats models can offer us, all the different functions that are available, that Python can do so many different things that we have to subset what we're interested in, otherwise we'd run out of memory on the computer, particularly on a Raspberry Pi, and it would grind to a halt. So we just pick the bits we're interested in. Let's import them. Okay, now you can see here we've got 3 different data sets. We've got the US city violent crime rate. We've got a bunch of crime rates for a bunch of different cities. We've got the police funding. So here we've just got how much each of those cities spends on police funding. And then finally we've got the youth unemployment from those cities as well. And what we're going to ask is, can these 2 factors explain some of the variability in the crime rates? And what we're going to do is do some basic manipulation of that data to get it into a format that the stats models, the SM function, can use to produce an ordinary least squares regression. And essentially what this is doing is putting both of our variables together into one data set. We then ask the ordinary least squares regression to be performed using our X, which is our combined data set, and our variable that we're trying to explain, the US city violent crime rate. That produces some output that's in model, and then what we can then do is run that analysis to get the results we're interested in. And on the next slide we'll plot it. So what I'm going to do is just copy all of this in to Python, and you can do the same. The PowerPoints will be made available So as you can see, it's created a bunch of different variables. We can look at what the values of this variable are. You can see that those are the values we gave it. So what we're doing here is a different way of inputting data into Python. Rather than just getting it to generate a list of numbers for us, we're specifying those numbers. So using NumPy and telling it we want to produce an array, so a list. We then put a list held between square brackets separated by commas for the values we want. Okay, so we've run through this. Let's look at the next slide. Here what we want to do is to plot the data. And there's a mistake on this slide that I'll quickly address. We don't want the variable we're plotting to be US violent crime rate. We want it to be called US violent crime rate. We don't have a variable called Y. So here we're saying, using the plotting function that we've already looked at, plot the values held within this variable in red and just label them within the computer US city violent crime rate. And we can later use that label to produce a legend. So let's copy that in. The second thing we want to do is plot the output of our least squares regression. So as you'll know, if you've got two explanatory variables, the output of your least squares regression will have 1, 2, 3 things. You'll have a constant and then a value to multiply by your two input parameters. And that's exactly what this does. Here we're going to say, well, we want this line to be in blue, and again we're giving it a label that we can use to display in the plot in a minute. So we've produced that. Now we want to do this. We want to create a legend, and what that will do is automatically look and see if there are any labeled sets of data. If there are, it will pull them out and use those labels for the legend. And then finally we want to display that data, show that data. And what you can see here is our crime rates are in crime rates are in red, and our attempt at trying to explain those crime rates using police funding and youth unemployment come out in red. So you can see it does a fairly good job of explaining some of the variability. The social science behind that isn't what we're looking at here, but you can imagine how you could use this tool to work with incredibly large data sets to do statistical analyses. Here we're not looking at big data sets, but imagine doing this with millions of pieces of data. You wouldn't want to attempt it in SPSS or Excel. This would be a tool to do that. And it would be no more complicated than what we've done here. So the next thing we want to highlight is that arrays, these lists of numbers, they're not necessarily just a simple sequence of numbers. They're not just 1D. So if you think about a lot of the analysis that's done in environmental sciences, in physical geography, and any sort of aspects of modern science, these data sets are big and they're spatial. Spatial data comes in at least 2 dimensions, latitude and longitude. We'll often have a Z dimension, a third dimension, height. It may well have a fourth dimension, time. So we don't need to start thinking about the ability to operate with data sets that have at least 3 or 4 dimensions. Now this is something that's very, very hard to do in Microsoft Excel. Excel is very good at visualizing 2D data sets because you've got along the page and you've got down the page. Working in more dimensions, you need to essentially use tools like scientific computing. So let's create a simple one-dimensional array. Hopefully you'll be familiar with this idea now. So we've just copied that across. We've got an array called myArray that's just a list of 6 numbers, 1, 2, 3, 4, 5, 6. Obviously we can plot that, as you saw before. It's slow because we're on a Raspberry Pi, but still works fine. So, this is how you visualize a one-dimensional piece of information. That's nice and straightforward. Okay, now we can move into 2-dimensional data sets. Now obviously this is key because we want a spatial element to this, for example. So again, we can have a similar command to we had before. NumPy array, we create an array. it's like what we saw before, just a sequence of numbers, but we have multiple sequences of numbers. So this is one dimension, it's repeated in a second dimension. So let's copy that in. Now we can look at what that looks like. We can print my array. And what you can see here is something that looks a bit like some values in an Excel spreadsheet. That's because an Excel spreadsheet can hold two-dimensional data, columns and rows. But what we can do in using Python, using a lot of scientific computing tools, is to visualize that data. So I'm going to produce a contour F, a filled contour plot. So imagine a contour plot like a map. I'm going to produce one where the colours represent the areas between the lines are filled with a colour, and the colours represent the values we're interested in. So we're producing that, and we now need to display it. So what you can see is we've got information in two dimensions, but the values that are stored in those in that two-dimensional array are represented by colours. I haven't produced a colour bar here to tell you what the colours are, but the reds refer to high values, to 4, the blues to low values, so 0. If you look here, you can see the same thing produced with a colour bar. It's actually a very straightforward thing to do. We can add a colour bar by going plot.color bar, spelled the American way. And then we can again display that. And you can see the same thing with the colour bar. Okay, so this is visualizing a contoured data set, visualizing two-dimensional data as contours. And actually, if you think about what this is very much like a lot of the climate model data you'll have seen, a lot of sea surface temperature data. A lot of spatial data sets will be presented in this way. And you can see in Python it's very, very simple to do that. Okay, let's move onwards. Now, occasionally, and I don't often find myself doing this, but occasionally you might want to visualize data in different ways, not using contour plots. You might want to actually sort of visually represent it in 3 dimensions. Now this is also possible, and you might want to do that because your data set has more, say a 4-dimensional data set is very difficult to visualize on a piece of paper. You might want to have the colors representing 1 dimension, X and Y representing the 2 other dimensions, then a 4th dimension being represented by a further axis. So this is just an example, again from that Matplotlib gallery. You'll be able to see how these things can be done. So here we can represent 3D and 4D data fairly cleanly, although it's often hard to interpret things that way. Okay, the next point I want to make is that whilst we're putting information into these arrays, we can also extract that information. We can look at items that are at a certain point within an array by using indexes. So let's create an array, and this time let's make that array contain words rather than numbers. So our array contains the words cat, dog, and elephant. Sorry, I pasted it twice because it's a bit slow to catch up. Let's print my array. Okay, it's a list of information. First element is cat, second element is dog, the third element is elephant. So what we might want to do is to print the first item. So the first item is going to be cat. Well, how do we specify the item we want to print, or we want to extract to do something with? Well, we use square brackets. That's basically a way of saying I want to give you an index value, and I want to pull you out I want you to pull out the piece of information that relates to that value. Now, something you might well have already learnt about Python is that it starts counting from 0. So the 0th item, the 0th item, is actually the first item in any list. So we give it the value 0, we get cat. We give it the value 2, we get elephant. So this is particularly useful. You can create sort of dictionaries effectively. You can store information away and you can pull it back. And of course you can do clever things like pulling out ranges of data. So between 0 and 2 means from the first item to the item prior to item 2, and it gives you a range, gives you both of those items, the first and the second item. So there's a whole bunch of things you can do here, and these are really just tools that you need to be aware of, and you'll put them to practical use later in your work. One further thing we need to talk about are loops. Now, Code Academy will teach you about loops, but I just want to highlight in a simplistic way how these work. Loops allow you to do what the name suggests and loop through, so repeatedly go through a data set. So what we're going to do is step through each item in the array and pull out that item one by one. And the way we're going to do this is say we're going to provide a command for something we call a for loop. We're going to step through a list of numbers. The list is going to be described by the words range 3. So let's look at what range 3 means. Range 3 is a list of numbers 0, 1 and 2. So what this is going to do is going to step through, taking the first item in that, referencing, indexing our array with that first item, so it's going to pull out the item corresponding to an index of 0. It then moves to the next item, 1, and pull out the index item relating to 1, which will be dog. Then it will pull out the value 2 from our list of numbers, index our array with that, and pull out this third item, elephant. Now, you can see that I is here. I is just a variable that this loop is using to hold this temporary piece of information. So I is holding the values 0, and then 1, and then 2, and passing that information to our array. So let's try that. For I, this could be anything. This is just an arbitrary variable name in, so it's holding the values sequentially in our array. So our array is going to contain, let's do it simply. Let's just make it contain the values 0, 1 and 2. It's just an array. For those values, sequentially, print out the corresponding value from my array based on that index. And what you can see is it's gone through one by one, pulling out that information. Now, it's not obvious there that it's gone through this sequentially. What we can do is actually ask the computer to wait for a short period of time between each. So to do this, I'm going to import a module called time. Time allows you to do a variety of things, but amongst those things are just waiting. So time.sleep 2. And what that says is each time it goes through this loop, just do nothing, sleep for 2 seconds. What you can see here now is that every 2 seconds it's going through that loop again, pulling out a further piece of information. Now there's a whole bunch of other things I want to just quickly highlight to you. The first is how you start to interrogate what commands are available to you. And realistically, the way you do this is just to get onto Google and try and search for a command to do what you want. An alternative is to ask NumPy to display all of the items it has. And what we do there is say, well, give me a directory, dir, dir, containing all of the commands that NumPy can do. So this is useful if if you know that NumPy can do something and you can't remember exactly what the name of it is. And what you can see here is that there's a whole range of things that NumPy can do. We're not gonna mess around with them, but what you can also do is ask NumPy what these things are. So we can go help NumPy dot, pick one of these, NumPy dot where, that's a very useful function actually. And this provides us with the help page associated with that. So you can read this through. And it's often very good, it often gives you examples of what things do. And once you've looked at the help, you just press Q for quit and it takes you back to where you were. Okay, there's a few more commands I want to explain to you. And here we're just trying to expose you to a few things so you're aware of the sorts of things you can do. Don't worry too much about the details. So we've got an array, got a list of numbers. Here it's only a few numbers long, but in practice it could be, you know, tens of millions of numbers in a multiple dimensional array. We did means, we did maxes and minimums. Well, another thing you might want to know is how big this array is. So we're going to print numpy.size. Again, you know, nice, simple, descriptive name to this function. And we can see that this array has 5 elements in it. We've performed means already, but let's just do that again. And let's just do it to show, to sort of reiterate the point that you can hold data in variables that's had some mathematical function performed on it. So my mean is our new variable that will hold some information, numpy.mean, my array, numpy, np.mean, and my mean will hold the mean value from the other array. So we can print that out, my mean. There we are, there's the value. You know, also you can do loads of different things. So numpy.round my mean, and we want to hold this information in a new variable called my rounded mean. I think you can probably guess what this is going to do. It takes 48.4 and it rounds it to the nearest value, 48.0. And of course you can do things like, let's print this, numpy.power, so you can put the value 48, which is my rounded mean, which is just a value held in a box called my rounded mean, and we want to cube it. There we are, we want to put it to the power of 8. These things are completely, you know, basic mathematical functions are just there and easy to use. We've already looked at the fact you can multiply arrays together, but we looked at it with a rather large array. So let's just think about something we can visualize more easily. So array A, or array 1, is equal to a bunch of values, 1, 2, 3, 4. Let's make a second array called array 2. And let's make each of these values equal to 3, just so we can quickly evaluate whether the maths is doing something sensible. So we can print array 1 times array 2, and we can see that each value in the first array is multiplied by its corresponding value in the second array. Each value has been times by 3. Now if we make array 2, you know, that's 3, that's 2, that's 1, that's 0, do the same maths, we can convince ourselves that they're not all being multiplied by 3, they're all being multiplied by their corresponding element in the list. So 1 times 3 is 3, 2 times 3, sorry, 1 times 3 is 3, 2 times 2 is 4, 3 times 1 is 3, 4 times 0 is 0. But of course we can't just do multiplication. You know, we may want to look at, say, the difference between two big data sets, the same way as you would subtract one column from another in Excel, and we can say array 1 minus array 2. So 1 minus 3 is minus 2, 2 minus 2 is 0, 3 minus 1 is 2, 4 minus 0 is 4. Lots of different things you can do. I'd encourage you to have a play. Now, a previous loop example just pulled out a piece of information sequentially. Well, often what you want to do is loop through a data set and perform often a fairly complex piece of mathematical analysis on each item sequentially in that data set. But to highlight that, what we're going to do here is just do a very simple mathematical function on each element in that array sequentially. So 4, and here we're not going to use I, we're going to use item as our variable that holds the pieces of information in array 1. Now this is something that Python's particularly good at, so I find very, very valuable actually. Rather than just sequentially moving through things and using an index to specify later on what you're doing, you can actually just pull the elements of the thing you're interested in out one by one and do something with them. So item is going to hold each of the different elements within our array 1 sequentially. And it's going to print the value of that item times by 2. So it's basically going to double it. And to prove that it's going through one by one, we're going to do time.sleep 1. We're going to wait for 1 second between each step. Press enter again, and it runs through that loop. So you can see it's performing that function. Now, if you think about what a climate model might do, it splits the world up into a whole bunch of these different boxes representing different areas in the atmosphere and the ocean. And actually what we do a lot of the time is to just loop through each of those boxes and perform some mathematical function. Multiply the heat within that box by something corresponding to the heat coming in from the surface at the corresponding atmospheric box. So you can start to see how you can deal with spatial data sets quite powerfully using these loops. There's loads of other things you can do. You can start to add things to and take things away from arrays. So here we've got my array is equal to just a nice simple array, 1, 2, 3, 4, that we keep coming back to. Now I just want to add a further element to that. So we're going to say my array is equal to the same array but with number 5 appended. So numpy.append, if I can spell it right, my array, and it does exactly what you think. It's going to take my array and it's going to append the value 5 to the end of it. So print my array. And we can see it's gone from being a list of 1, 2, 3, 4 to 1, 2, 3, 4, 5. And we can append 50 on the end. And you can see how you might be able to combine this with a loop to keep adding things as you want them. Similarly, you can delete things. You can do all sorts of complex functions, treating arrays as boxes into which you're taking, putting into and taking out information. So we looked at the help information for the numpy.where function. Now this is something that's particularly useful, again, in spatial analysis. Imagine that you had lots of information that was held in latitude and longitude space, and you just wanted to look at the high latitudes. You might say, I want to only look at the elements where the latitude is greater than 60, for example, with the longitudes greater than 180. So let's look at how we might do that with our simple array. I'm just going to copy this array here because it's a little bit more lengthy than our previous one. So we've got our array sequence of numbers 1, 33, 4, 39, 22, 14, 19 and 0. So I just want to pull out the location where the values in my array are greater than 20. It's kind of a simple logical command again, and we can print those locations. So we can see that the item, the number 1 element, so that's 0, 1, yep, that's greater than 20, and then 3, 0, 1, 2, 3, 39 is greater than 20, and the next one, 22, that's greater than 20. None of the elements are. So this is great. We're starting to pull out just those things we're interested in. And obviously you can do much more complicated things here. Now, there's a few things that I want to highlight towards the end here that I just want you to be aware of because they could trip you up. So let's go through this example. Oops. So let's copy in the standard array we've been using. Let's look at that array. So the contents of it, just the values 1, 2, 3, 4. Now, one thing we can do in Python, and this is unique to Python and it's done for very good reasons, but it can cause confusion, particularly actually if you've used other programming languages before Python. What you often want to do is assign some values from one array to another array. Typically, when you do that, you're intending to copy that item. So let's see if that works in Python. So we've got another array equal to my array. You might think that takes the information from here, copies it into that one. So what we can now do is change one of the items in that array. So we're going to specify that we want to look at item number 2, so the third item in the array, and we're going to reassign that. We're going to give it a value of 100. Now, if we print our array, as we'd expect, it was 1, 2, 3, 4, but we've replaced element number 2 with 100, so it's now become 1, 2, 104. Now the thing I want you to be aware of is if we now go back and print my array, that looks the same. So this function here, which to some of you who are more familiar with programming might look like you're copying one array into another, is actually just linking them together. It's saying, well, these are identical, the information these are identical, we've just got two different descriptions, two different names that we're going to assign that both reference that box with some numbers in it. It's not a copy. If we want to copy it, we have to go myArray.copy brackets, and then at that point we can change a value in another array. Let's make that one. Let's make item 1 100 as well, and then we can see that these two arrays are different. Okay. And that's described on this slide, as is the way of copying. So that's been a little highlight of some of the things that can be done within Python. There's an awful lot more that can be done, and I would suggest you go to Google to find out how to answer specific questions. The best way to learn Python is to try and take on a specific task, and that's what we'll be doing in the coursework.